Okay, we'll conclude this unit of study with two final example problems on the addition of velocity vectors in two dimensions. So whenever performing problems of this nature, it always references two different frames of reference for viewing a moving object. So the first example describes a plane that's capable of flying at 160 meters per second in calm air, and it points its nose due north. So by stating how fast it can go in calm air, what we're really saying is the 160 meters per second is going to be the velocity of the plane with respect to the air. But at the same time, there's going to be some velocity of the air with respect to the Earth. So that's described here. There's a crosswind of 30 meters per second blowing due east. How much time will it take to fly over a city that's located 80 kilometers to the north of the airport? How far east will the plane drift during that time? What's the velocity of the plane with respect to the ground in magnitude and direction notation, and also in unit vector notation? And lastly, what if the pilot doesn't want to drift to the east or to the west and instead arrive at the airport that's directly due north of their origin location? Then what heading should the pilot take? So take a moment, reread the problem, identify any important numerical values, and start to picture how you could represent this problem graphically on your paper. Okay, so you can work along with my solution, see if your diagram looks anything like mine. There's an airplane that points its nose due north. And there's a city that's located somewhere along a line that lies to the north. So that distance from the plane's origin to the final destination lies along, we'll call it the y-axis. So I think it's fair to say the north-south axis is our y-axis and the east-west is our x-axis. So there's a displacement of 80 kilometers along the positive y-axis. And then there's a crosswind due east of 30 meters per second. Okay, I've got this. Let's use a red for the velocity of the plane with respect to the wind. Okay, so we'll label that VPW. And then we'll use green. How's that? Okay, now I've already connected my vectors tip to tail, so they're in an orientation that allows me to consider some graphical vector addition. There's the velocity of the wind with respect to the ground. So what we're really looking for is what's the velocity of the plane with respect to the ground. And that's really just found by adding the other two vectors together. We can state that as an equation. The Galilean Transformation tells us the velocity of the plane with respect to the ground is equal to the velocity of the plane with respect to the wind plus the velocity of the wind with respect to the ground. So let's state all of this in unit vector notation to start with. Okay, so it's fairly simple. When any velocity points directly along the north, south, or east-west axis, then it has its full magnitude is the component of one of its types of motion, and the other type of motion is zero. I should just show you what I'm talking about here. For example, the velocity of the plane with respect to the wind has zero component along the x-axis, right? It points entirely along the positive y-axis. So we say this is represented in unit vector notation as 0 meters per second I hat plus 160 meters per second j hat. The velocity of the wind with respect to the ground also has a zero component, but the zero component for that one lies along the y-axis. So this is positive 30, did I get the number right? Yeah. Positive 30 meters per second I hat plus 0 j hat. And so by putting it in unit vector notation, it makes it very easy for us to perform the vector addition. We can just really do scalar addition down the columns. So we find that the velocity of the plane with respect to the ground is equal to 30 meters per second I hat plus 160 meters per second j hat. So we're going to have to figure out then how that translates in terms of angle and magnitude. But in this case, it shouldn't be difficult because this special case forms a right triangle. Now, key note here, several of the examples you've seen along the way can be illustrated by way of a right triangle, but that's not always the case. So I think in our second example problem, we'll see how we can ask a slightly more challenging problem when right triangles are not formed by the addition of velocity vectors. Okay, we haven't really answered part A yet, have we? How much time will it take to fly over a city 80 kilometers to the north? So since we're given a displacement to the north, we could just use the dirt equation since this is constant speed, and we can't mix and match, right? Information about a distance to the north can only be combined with the northward component of velocity in order to figure out a time. In other words, time can be found by taking a horizontal displacement divided by a horizontal velocity, or an overall displacement divided by a total velocity, or what we want to choose here, a vertical displacement divided by a vertical velocity. So this is nothing more than taking 80,000 meters, right, 80 kilometers as our displacement, and dividing it by just the component along the y-axis. So divide 80,000 by 160, and we end up with 500 seconds. Kind of hard to relate to 500 seconds, right? Let's divide that by 60. And we get 8.3 minutes. Okay. No reason to do that other than just be able to relate to the amount of time more conceptually. So there we have it. Part A is complete. Part B, how far to the east will the plane drift? So again, we're using the dirt equation, but now we're asked about information along the east-west axis, so we treat motion along the x-axis independently from motion along the y-axis. So when we rearrange the dirt equation, now we have the displacement along the x-axis is the horizontal component to the overall speed multiplied by time. Now that we know the time is 500 seconds, then we can match that with the 30 meters per second of horizontal speed. 30 meters per second for a total time of 500 seconds gives us 15,000 meters, which we'd better state as 15 kilometers. Okay, part C. We've already given the velocity in unit vector notation. Here it is. So now we have to represent that in magnitude and direction. So let's use this diagram as our guide. The magnitude of the overall velocity points at an angle, and it's comprised of this northward component and eastward component. I'm not sure I really drew this to proper scale. I don't think the angle is quite this large. After all, this was given as 30 and this is 160. But in any case, it's just a matter of using the Pythagorean theorem. The total speed, or in other words, the velocity of the plane with respect to the ground in magnitude is just the square root of 30 squared plus 160 squared. It's visually represented as the hypotenuse of a right triangle. So we get about 162.8 meters per second. Oh, but that's not quite right. We have to give both a magnitude and a direction. So we need to say at some angle. So we're describing the angle here. That's probably not the way we want to describe it, is it? It's better that we state the angle relative to the positive x-axis, relative to eastward. Okay, so then in that case, the side opposite the angle is the 160, and the side adjacent is the 30. Tangent equals opposite over adjacent, so we need to take the inverse tangent of 160 over 30, or 16/3. So we're taking the inverse tangent of 5.3 repeating, which gives us an angle of 79.4 degrees. Now we could call that 79.4 degrees north of east, or I guess it would be just as well to say 10.6 degrees east of north. That's a little less typical. But when we don't state the compass directions and we just give the angle, then it's always implied to be relative to the positive x-axis. Okay. So last thing, how could the pilot how could he point the nose of the plane so that there is no drift to the east? Let's say the airport is actually located not just along a line that's 80 kilometers to the north, but is actually located due north from the destination, or the destination is due north from the origin airport. Okay, so our diagram will look a little different in this case. Let me make some room here. Here's our next problem we want to solve. So get that out of the way. There we go. Still part D of our first problem. There's the destination, there's the origin, and so the plane is going to have to fly somewhat, not entirely, but partially into the wind so that a component of the plane's velocity cancels out the wind velocity. So again, we'll color code this. Red is the velocity of the plane with respect to the wind, VPW, and that still has a magnitude of 160. And then added to that is this east-west wind blowing to the east with a magnitude of 30. There's the velocity of the wind with respect to the ground. And so now when I add these by connecting the tail of the original vector to the tip of the second vector, what we should have is a vector that points due north. Okay, so again, this actually does form a right triangle, but this time it's not the velocity of the plane with respect to the ground that forms the hypotenuse, it's the velocity of the plane with respect to the wind that makes our hypotenuse. So slightly different. Some people would be tempted to guess that this angle right here is the very same 10.6 degrees, but this time west of north instead of east of north. But it doesn't have that sort of symmetry to it. It might be close, but not exactly. So how do we do this one? Well, again, the Galilean transformation. The velocity of the plane with respect to the ground is the velocity of the plane with respect to the wind, plus the velocity of the wind with respect to the ground. So let's try to state the velocity of the plane with respect to the wind, the velocity of the wind with respect to the ground, and then just know that when we add these together, that'll give us the velocity of the plane with respect to the ground. So the velocity of the plane with respect to the wind, well, gosh, if we knew what this angle was, see, that's what we're trying to solve for, but if we knew what it was, we could take that vector that represents the 160 meters per second, we could sketch it so we see its tail at the origin of the xy axes, and then we could picture its components, project to the y-axis, project down to the x-axis, and we'd have a westward component that's just the side of a right triangle, and we'd have the northward component that's also the side of some right triangle. So if we call this 160 meters per second at an as of yet unknown angle, the northward component would just be 160 times the, well, let's see, in this case, the 160 lies adjacent to the unknown angle. So SOHCAHTOA, the cosine is the one that makes a ratio between adjacent and hypotenuse. So by multiplying 160 times the cosine of this undetermined angle, we have the vertical component to that velocity vector. And so likewise, the horizontal component is going to be 160 times sine theta. So the role of sine and cosine as far as determining horizontal and vertical components might switch. If you recall projectile motion in the first example problem of kicking a soccer ball over level ground, we defined an angle of kick, and one of our first steps was to break that velocity into components. And I think in that case we said the vertical component was the overall velocity times the sine of the angle, and the horizontal was the velocity times cosine. So in this problem with the soccer ball, we associate cosine with the horizontal component, whereas this problem with the plane, we're associating cosine with the vertical component. Well, that's just because in our example with the soccer ball, we were measuring angle off of the x-axis. When we change and measure angle off of a y-axis, the role of sine and cosine get reversed. So don't get locked into thinking that cosine will always give you a horizontal component. Sometimes it gives you a vertical component. Make sure you're representing all of your vectors graphically, and you'll avoid making some common mistakes. Okay, so the velocity of the plane with respect to the wind has a component of negative 160 sine theta I hat. You understand why I say negative? Because it's pointing to the left. Plus 160 cosine theta j hat. The velocity of the wind with respect to the ground hasn't changed from the original setup. It's 0 I hat. Oh, sorry. 0 j hat. It's positive 30 I hat plus 0 j hat. Now in the end, the velocity of the plane with respect to the ground, because we know it arrives at the destination exactly due north without drifting along the east-west axis, the overall velocity has to have 0 component along the east-west axis. And then this is going to be plus, well, let's see, it just has to be plus 160 cosine theta j hat. That doesn't help too much. It still doesn't give us this value of theta. But we ask ourselves, how could this possibly work out? How could negative 160 sine theta combined with positive 30 give us a result of 0? Okay, negative 160 sine theta plus 30 has to equal 0. So sine theta has to be equal to 30 divided by 160. Right, let's add and a quantity to both sides of the equation, divide on both sides of the equation, right? Just a couple steps of algebra. Okay, so if we take the inverse sine of 3/16, we get about 10.8 degrees. So the plane would have to head 10.8 degrees west of north in order not to drift at all. Now that I know this is 10.8, if I wanted to, I could plug that in for theta here, and I'd have the velocity of the plane with respect to the ground in proper unit vector notation. The problem didn't ask for that, so there's no need to go on. We're just asked what heading should the pilot take. Now another way to answer it, instead of saying 10.8 degrees west of north, we could picture that on our compass, something like this. So that angle right here is 10.8 degrees, but don't forget we had to get to 90 degrees off of the east axis just to get to north. So we could add 10.8 plus 90 and get a heading of, we can just say the heading is 100.8 degrees, end of story. Okay, here's our next problem. Some boat can reach a cruising speed of 30 meters per second in calm water. Once again, that's giving the speed of the boat with respect to the water. So the captain takes the boat out into the ocean where the water isn't calm, there's a current. he heads out for an island that's 12 kilometers away, and that island is located due north from his origin location on the map. He finds that he has to take a heading 15 degrees west of north in order to cruise directly to the destination without drifting along the east-west axis. The total trip takes 10 minutes. What's the speed and direction of the ocean current? So this sounds a lot like our previous problem. We're just being asked in a slightly different way. So we're given the heading of the boat. The captain sets out at an angle of 15 degrees. See, there's north, so 15 degrees to the west of north, right? In doing so, the boat its nose might point into this second quadrant, but it doesn't travel along this line, right? Its displacement isn't represented by this vector. Its velocity is represented by this vector. It actually continues to point its nose along that direction, but its actual displacement is just this steady northward drift until it reaches a destination 12,000 meters away in a time of 10 minutes, or maybe better stated as 600 seconds. Okay, so we get an idea of what the velocity of the boat is with respect to the water as well as with respect to the earth, or to the shore, if we want to say. So yeah, if we were to divide 12,000 meters, that's a displacement along the y-axis, by a time of 600 seconds, then we get a velocity along the y-axis of 20 meters per second. Okay, so I think that's really representative of the velocity of the boat with respect to the Earth. Whereas the 30 meters per second here is the velocity of the boat with respect to the water. And so the question is, what's the speed and direction of the ocean current, which is really a way of saying what's the velocity of the water with respect to the Earth. Okay. So our Galilean transformation says the velocity of the boat with respect to the Earth is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the Earth. So velocity of the boat with respect to the Earth, velocity of the velocity of the boat with respect to the water, velocity of the water with respect to the Earth, when added together, gives us the velocity of the boat with respect to the Earth. We'll fill in whatever we can here. Let's see, the velocity of the boat with respect to the water. We've got that. We're told the magnitude and the angle. So this is going to be negative 30. See how we can just skip here? That represents, if I trace that same vector and slide it from here up to here, it stays the same length, points in the same direction, and appears to be the side opposite an angle in a right triangle. Okay, so negative because it's pointing to the left, and because it's the opposite side of an angle in a right triangle, we can say this is negative 30 sine of 15 degrees. And then the component along the north-south axis is adjacent to the 15 degrees and points in the positive direction. So plus 30 cosine of 15 degrees. Oh, sorry, I forgot my J hats and my I hats. The velocity of the wind with respect to the Earth, well, that's the question at hand, right? We don't know anything about this one. But we know the velocity of the boat with respect to the Earth, right? Overall, it doesn't have any component of motion along the east-west axis, so this has to come out to 0 I hat. And then it only has motion along the y-axis, so that it travels 12,000 meters in 600 seconds, so it has a velocity of 20 meters per second. Okay, so grab a calculator and let's just replace these quantities with exact numerical values. So take the sine of 15 degrees, multiply it by 30. So here we have negative 7.76. So this must be positive 7.76 if the result of adding those together comes out to 0. Okay, so we've got part of the motion of the velocity with respect to the velocity of the wind with respect to the Earth. Okay, and then the other one, let's see, the cosine of 15 degrees multiplied by 30 gives us 28.98. Okay, 28.98 combined with what would give us 20? So this must be negative 8.98. So there we have it. At least we've got the velocity of the wind with respect to the Earth in unit vector notation, but we're asked to give it in magnitude and direction notation. So the fact that it's got a positive component along the x-axis and a negative component along the y-axis helps us picture it, right? It's pointing essentially to the right and downward. So that vector would represent the velocity of the wind with respect to the Earth. This vector represents the velocity of the boat with respect to the wind. That was the 30 meters per second we were given. This still remains a question. And this vector pointing due north, that represents the velocity of the boat with respect to the Earth, velocity of the boat with respect to the water, velocity of the water with respect to the Earth, and this one we know it comes out to 20 meters per second. So what's this? Well, you say, wait a minute, that's not a right triangle. Yeah, I know it doesn't matter, but we've got its horizontal and its vertical components. So without even drawing in these vectors, we just see we have the velocity of the wind with respect to the Earth. This vector has a component to the right of 7.76 and a component downward of 8.98. And so if we slide these vectors around, we see a right triangle, and we can just use the Pythagorean theorem and take the square root of 7.76 squared plus 8.98 squared. And we get about 11.9 meters per second. Now we want a direction. So we can say how many degrees south of east. So tangent of that angle would be 8.98 over 7.76. And we get an angle of 49 degrees south of east. So there's one way to answer it. The velocity of the wind with respect to the Earth is 11.9 meters per second at an angle of 49 degrees south of east. The alternative would be to add the full 270 degrees towards south plus the complement to that 49 degrees, which would be 41 degrees. So 270 plus 41 would give us, what, 311. So we could just say 11.9 meters per second at 311 degrees. Those are two ways of saying the same thing. Okay, so thanks for tuning in. That's the end of our unit on motion and two-dimensional motion. Thanks for watching.